Neighborhood functions. Neighborhood functions are used to find the characteristics of the vicinity, which means the neighborhood of any location. This means we not only want to find what is at a particular location, but also what is near to that location. So to perform the neighborhood analysis, we must first state which target locations are we interested in, and then also define their spatial extent. That means how much those locations have been spread. So we first define that these are our target locations and this much is their extent. Second thing we define is how to determine the neighborhood for each target. That means according to you, what is the neighborhood for that target? Is it the 500-meter distance from the target which you consider as the neighborhood? Or you consider a 10-meter distance from the target as the neighborhood for the target? Or you consider a 2-kilometer distance from the target as the neighborhood for the target? So you must first define according to you what is the neighborhood for each target. Third thing you will define is what do you want to determine, or which characteristic do you want to compute. So what are you looking in this neighborhood? Say for example, we'll take an example of a target which might be an ATM, a nearby ATM, and we want to find out its neighborhood. So our target may be an ATM or maybe a medical clinic. In this book, the example given is of a medical clinic. So whatever is our target, we want to find out in its neighboring area of around 2-kilometer distance. Okay, which are the other banks, or in 2-kilometer travel distance, what are the different things in 2-kilometer travel distance of this ATM or of this medical clinic? Or if we are talking about the medical clinic, then which are the hospitals in the 2-kilometer distance from this medical clinic? So like that we can find out many things by first considering what is the neighborhood and then trying to find out the characteristics for that neighborhood. Determining neighborhood extent. Now how do you determine the extent of the neighborhood? One way of determining a neighborhood around any target location is by making use of some geometric distance function. For example, you want to find out how the pollution is spreading through the rivers or through the air, through groundwater flow, or any weather systems. What kind of weather conditions are there? So there are more advanced techniques for computation of flow and diffusion. What we mean by flow and diffusion, let's understand that first. So first thing is diffusion function. Diffusion function is based on the assumption that a phenomenon is spreading in all directions. Say for example the pollution or any release of gases which are getting released from some factory. So how does it spread in all directions? If you want to find out that, then you might need diffusion function. It might spread in all directions, but not necessarily equally in all directions, because it depends on what kind of weather conditions or what kind of resistance it is facing while it is spreading in all directions. Now the resistance depends on the terrain characteristics, the local terrain characteristics. what are the weather conditions, or what are the terrain characteristics of that location. The second one is flow computation. Flow computation means the phenomena is going to spread, but it will choose a particular path. This path is the least resistance path. That means it is going to choose a path to flow out of the different paths, depending on which path is providing it the least amount of resistance, and it will not spread in all directions. So both the flow and diffusion computations take into account the local characteristics, the characteristics of the locality, and therefore it is easier to perform these kind of computations on raster data. Proximity computations. In proximity computations, we are going to use some geometric distance function to define the neighborhood of one or more target locations. So we are going to take one or more target locations and try to find out what is the neighborhood of that particular location. So there are different techniques of finding out the neighborhood. The most common and useful technique is buffer zone. We are going to look at another technique also. So let's first look at the buffer zone generation. Buffer zone generation. Now what do you mean by buffer zone? We have one or more target locations and we want to determine the area around those locations within a certain distance. So you can see in this figure A, there are a number of roads, there are a number of main roads, and there are some minor roads also. So they are selected as targets. You can see over here. The main road is selected and it has been given a buffer area of 75 meters, whereas minor roads have been given the buffer area of 25 meters. Sometimes we may also want to find out zonated buffers, which means we want, say for example, we want to find out to what extent will the noise spread from the roads. So as you can see over here, we are marking these roads into different buffers. Okay, as you can see, the description of the figure shows here that there are different zones in this figure at 100 meters distance from the road, at 200 meters distance, and at 300 meters distance. So we might want to show the buffers surrounding the main roads or maybe the minor roads also. Okay, and then what we are going to do is, after generating the buffer, we are going to save them in a separate layer, and as you can see, the buffers themselves are polygon features, so they will be stored in a separate data layer, and this data layer can be used later on for further spatial analysis. Now, how is the buffer generated in case of raster based data? First of all, the target location or the locations are always represented by selecting some raster cells. And then how do you find out the distance between different raster cells? Of course, it all depends on the kind of resolution that we are having for the cells and how much does one cell represent, like is it 1 meter or 1 foot, or how much is it? Depending on that, the distance from our target cell to other cells is computed to find out, say for example, you want to find out a 2 kilometer distance from a particular location. So A 2 kilometer distance is computed by taking the target cell, which is our cell from where we want to compute the distance, and then we go on adding the number of cells to it so as to reach a 2 kilometer distance from this cell. Now this depends on the resolution of the cells. Based on that many cells will be added so as to complete a 2 kilometer distance. The moment we reach the 2 kilometer distance, we stop over there and we create a buffer zone. So how do you compute the distance from one cell to the next cell? First we need to find that, and then we go on to the next cell so as to complete a 2 kilometer distance. So what is the way of computing the distance? As we had learned earlier, to compute the distance between two cells, we take the cell centers or any one particular place in each cell. So usually we take the cell centers and we try to find out the distance between the centers of both the cells using a Pythagorean distance function. And once we find out that distance between two cells, similarly we go on finding the distance between the neighboring cells so as to reach a 2 kilometer distance. Now when we are trying to find out the distance between our target cell and the next cell, we try to find the minimal distance between the two cells. Thiessen polygon generation. Thiessen polygon is nothing but it partitions a geometric space based on the geometric distance in order to find out the neighborhoods. So what we are having is a set of points which are called as target locations that are spatially distributed. Now we want to find out which locations are nearer to which target locations. So we want to know for each location in our study area, to which target is it closest to. So we are going to generate polygons around each target location, which identifies which locations belong to this particular target. So let us now consider that the dots are the target locations, and we want to construct polygons around each target location showing which locations belong to this particular target location. So in the figure you can see already the polygons are drawn, but how are the polygons drawn? Let us understand that. We are going to take the target locations and try to join these two and then make a perpendicular, which is a perpendicular bisector. It is going to divide this line joining the two target locations into two equal halves at a 90-degree angle. Same thing will repeat for other two target locations. Again we connect them and then we try to generate a perpendicular bisector. So that perpendicular bisector might extend. Okay, and same thing we repeat for suppose these two target locations, and this repeats. But what we are going to do is, and let us suppose these two lines, and then we have a perpendicular bisector, but we are going to find out only the intersections, and hence since we are already finding out the intersections and then we are clipping those lines, what we get in the end is something like this. Now if you are already having a Delaunay triangulation for the same set of input points, then it becomes much more easier to construct the Thiessen polygon. As you can see in this figure, the triangulation is already made. We just have to find out the perpendicular bisector of each side of the triangle. So you can see that this is the side of the triangle and this is the perpendicular bisector, and same thing is repeated for all the sides of the triangles, of all the triangles, and then these perpendicular bisectors are combined to make these polygons, which are shown on the right hand side. So here we have the Thiessen polygon generated.